Welcome to the deep dive. We're doing what we do best here, taking the really interesting stuff you, our listeners, send us, and, well, digging deep to figure out what's truly important.
Exactly.
So you shared this Airframe Glossary.pdf, which, okay, might look like just a list of terms at first glance, but we see it as, a way into understanding the incredible world of aviation engineering and the really precise language they use.
It's a whole language, really, built on physics, material science. Safety is paramount.
Right. So our mission today is to navigate this terminology, find those maybe surprising connections between terms, and just give you a clearer picture of the principles and parts that make planes fly.
Yet, it's more than definitions. It's about understanding the system. And when you see how these terms link up, you realize each one's a vital piece of this huge puzzle.
Couldn't agree more. So where better to start than the big question? How does a plane actually get off the ground? You gave us airfoil.
Okay, airfoil. Yeah.
Now, you might picture just a wing shape, but the real magic is how it interacts with the air, isn't it?
Absolutely. An airfoil is really any surface designed to create a useful aerodynamic force, usually lift when air flows over it.
So not just wings.
Nope. Propeller blades, helicopter rotor blades, even parts of the tail sometimes, their shape, that cross-section, is key. Typically curved on top, flatter underneath.
And that shape is what creates the aerodynamic lift.
Precisely. The curve on top makes the air travel further, so it has to go faster.
Right.
Faster air, lower pressure, slower air underneath, higher pressure. That difference pushes the wing up. Lift.
That pressure difference. Simple concept, but so powerful. And the pilot can influence this lift, right? Which brings us to angle of attack and angle of incidence. They sound similar.
They do sound similar, but they're quite different. The angle of attack is the angle between the airfoil's chord line, that's an imaginary line from leading edge to trailing edge, and the direction the air is actually coming from, the relative wind.
Okay, so that's the angle the wing meets the air at any given moment.
Exactly. And the pilot can change this angle using the controls. Now, the angle of incidence is fixed. It's the angle the wing is actually mounted onto the fuselage.
Yeah.
That's set by the engineers during design.
So one is dynamic, pilot controlled, the other is built in. And knowing the angle of attack is critical for safety. There's an angle of attack indicator mentioned.
Very critical.
Yep.
Exceed the critical angle of attack, and the wing stalls, loses lift.
Yeah.
So, yeah, many aircraft have an angle of attack indicator right in the cockpit to help pilots stay in the safe zone.
It makes sense. Avoid the stall.
Ah.
Now, turning an aircraft, it's not always perfectly smooth, is it? We have the term adverse yaw. What's going on there?
Adverse yaw.
Yeah.
It's this tendency for the plane's nose to initially swing the wrong way when you start a turn.
Wrong way. Like, if I want to turn right, the nose goes left first.
Just for a moment, yeah.
Yeah.
It happens because when you use the ailerons to bank, say, you lower the right aileron to lift the right wing. That lowered aileron creates more lift, which is good, but it also creates more drag than the raised aileron on the left wing. So that extra drag on the rising right wing pulls it back slightly, causing the nose to yaw left initially. It feels uncoordinated.
Right, a bit sloppy if you don't correct it. So how do engineers fix that? Make turns smoother?
A couple of clever ways. One is differential aileron travel. The aileron going up moves further than the one going down.
So the upgoing one creates more drag to compensate.
Exactly. Balances things out. Another neat trick is the freeze aileron. Its hinges offset, so when the aileron moves up, its leading edge actually dips down a bit below the wing.
Oh, creating drag on that side too.
Yep, again, helps counteract that adverse yaw and keeps the turn coordinated. Very clever design.
Very clever. Okay, let's talk about changing the wing shape for different flight phases. We've got flaps and slats.
Right. Flaps are on the trailing edge, the back of the wing. Slats are on the leading edge, the front.
And they both basically increase the wing's curvature, or camber.
That's the main idea. More camber means much more lift, especially at lower speeds. Essential for takeoff and landing.
Makes sense. Need more lift when you're going slow.
Exactly. Flaps also add quite a bit of drag, which is actually helpful for slowing down on approach.
Good point. But you wouldn't want them deploying at high speed, I imagine. That leads to the flap overload valve.
Precisely. Deploying flaps or slats at too high a speed could damage them, or even the wing structure. So the flap overload valve is a safety mechanism in the hydraulic system that prevents them extending if the airspeed's too high.
A built-in safety check. Good. Now, shifting gears a bit to helicopters. We have terms like advancing blade and retreating blade. Lift on a spinning rotor must be complicated.
It is, yeah. The big challenge is asymmetrical lift.
Because one side of the rotor disc is moving forward with the helicopter, and the other side is moving backward against the direction of travel.
Exactly. The advancing blade moving forward sees a much higher relative airspeed than the retreating blade moving backward. Much higher airspeed means much more lift on that advancing side.
So the helicopter would want to tip over.
It would, if not compensated for. That's why helicopter blades are hinged. They can flap up and down, they experience aerodynamic drag forces, and pilots constantly adjust their pitch angle that's feathering.
Wow, constant adjustment. And blade track. Is that about making sure they all follow the same path?
Yes, blade track is ensuring all the blades rotate in the same plane. If one blade is flying higher or lower than the others, it causes vibrations and uneven lift. Needs careful adjustment.
Okay, back to fixed wing. Stability is obviously key. We have terms like canard, stabilator, elevens, vertical fin, dihedral, and tailets. That's a lot of stability components.
It is. They all work together to ensure the aircraft is stable around its three axes: longitudinal for pitch, lateral for roll, and directional for yaw.
So a canard, that's the little wing up front.
Right. It helps with longitudinal stability and control the pitching motion. A stabilator is a whole moving horizontal tail surface rather than just hinged elevators on a fixed stabilizer. More powerful pitch control, often.
And elevens combine elevator and aileron functions. Where do you see those?
Mostly on delta wings or flying wings where there's no separate tail. They handle both pitch and roll.
Makes sense. The vertical fin is the tail fin, providing directional stability like a weather vane.
Exactly. Keeps the nose pointed into the relative wind. And dihedral, that upward angle of the wings you see on many planes, that helps with lateral or roll stability. If one wing drops, the lower wing gets a slightly higher angle of attack, creating more lift and actually rolling the plane back towards level.
Clever passive stability.
Yeah.
And tailets. Small extra fins.
Yeah, sometimes added under the horizontal tail for a bit more directional stability, especially at high angles of attack.
Okay, so lots of design features for stability, but sometimes things get wobbly, like with Dutch roll. What is that?
Dutch roll. It's this kind of coupled oscillation, a combination of yawing and rolling. The nose sort of snakes side to side while the plane rolls back and forth. It's common in swept-wing aircraft.
Sounds unpleasant.
It can be disorienting, yeah. That's why many aircraft have a yaw damper. It's an automatic system that senses that yaw starting and applies tiny rudder inputs to damp it out before it becomes noticeable.
Like an invisible hand keeping things smooth. Now for fine-tuning. Trim tabs and anti-servo tabs. These help the pilot.
Definitely. Trim tabs are small surfaces on the main control surfaces, elevators, rudders, ailerons. The pilot adjusts them to counteract the aerodynamic forces so the plane flies straight and level without the pilot having to constantly push or pull the controls. Huge workload reducer.
So you can kind of set it and relax a bit more.
Exactly. An anti-servo tab is a bit different. You often find them on stabilators. It moves in the same direction as the control surface, but the airflow hitting it actually makes the control feel heavier.
Why would you want that?
It provides feel and prevents the pilot from over-controlling, especially at high speeds where controls can become very sensitive. It adds artificial resistance.
Okay, so one reduces effort, the other prevents overdoing it. Got it. What about slowing down or killing lift deliberately? We have spoilers.
Spoilers are panels on the top surface of the wing. When they pop up, they disrupt the airflow, drastically reducing lift and increasing drag.
So used for descending faster without gaining speed.
Yes, and also to help with roll control. Deploying spoilers on just one wing can help roll the aircraft. And crucially, on landing, they're deployed fully to dump the lift from the wings.
Why is dumping lift important after landing?
It puts the aircraft's weight firmly onto the wheels, which makes the brakes much more effective. You want friction with the runway, not lift keeping you floating.
Makes total sense. Okay, last one in this section. Stall strip. What's its job?
A stall strip is a small, sharp-edged piece, usually metal, fixed near the root of the wing's leading edge.
And it deliberately makes that part of the wing stall first.
Precisely. It forces the airflow to separate there at a slightly lower angle of attack than the rest of the wing. This ensures the wing root stalls before the wingtip.
Why is that beneficial?
Because the ailerons are out near the wingtips. If the tips stall first, you lose roll control. Stalling the root first gives the pilot some warning buffet and helps maintain aileron effectiveness longer, giving more control during the stall recovery.
A safety feature disguised as a small strip of metal.
Very cool. Okay, let's move on to the physical structure itself. Aircraft structure, materials, different wing designs first. Cantilever wing versus Pratt truss.
Right. A cantilever wing is what you see on most modern aircraft. It's strong enough internally to support itself without any external bracing, like struts. Very clean aerodynamically.
All the strength is inside.
Exactly. The Pratt truss is an older design, more common on early aircraft or some lighter planes. It uses internal spars held apart by struts, but crucially, it also relies on a network of tension wires.
Wires inside the wing.
Yep. Drag wires resist the backward pull of air resistance, and anti-drag wires resist forward forces, like when slowing down. It forms a lightweight but strong internal truss structure, like a bridge structure within the wing. Interesting. Now, the fuselage, the main body, monocoque and semi-monocoque. What's the difference?
Monocoque means single shell in French. In a true monocoque design, the skin itself carries almost all the structural loads. Think of an eggshell.
Strong, but maybe easily dented.
Exactly. That's why pure monocoque is rare in larger aircraft. Most are semi-monocoque. The skin still carries a lot of the load, but it's reinforced by an internal framework.
What kind of framework?
You have bulkheads, which are like walls dividing the fuselage into sections and giving it shape. Then you have formers, or frames, which maintain the cross-sectional shape. And running lengthwise, you have stringers, which stiffen the skin and prevent buckling.
So the skin and the internal frame work together. That makes sense. We also see fairings and fillets. They're all about smoothness.
Pretty much. Fairings are covers designed to smooth the airflow over junctions or components that stick out, like where the wings join the fuselage, or over landing gear. Reducing drag is their main job.
Making things more streamlined.
Right. Fillets are similar, often molded transitions, like at the wing root, again to smooth airflow and reduce interference drag. They might not be primary structure, but they help efficiency.
Okay. Inside the wing structure itself, we have the spar, cap strip, and web of a spar. That sound like the heavy lifters.
They absolutely are. The spar is the main structural beam running span-wise along the wing. It carries most of the bending loads the force is trying to bend the wing up or down.
Like the main beam in a bridge.
Good analogy. The cap strip is the reinforced top and bottom edge of the spar. That's where the tension and compression forces from bending are highest. And the web of a spar is the vertical part connecting the top and bottom cap strips. It handles the shear forces, resisting twisting and buckling.
So spar for bending, web for shear. Got it. And this connects to the idea of stressed skin structure.
Yes. In modern designs, especially semi-monocoque, the skin isn't just a covering. It's designed to carry a significant portion of the structural loads along with the spars, ribs, and stringers. It's an integral part of the strength.
Makes the whole structure more efficient. What about lightning holes? Cutting holes to save weight seems counterintuitive.
It does, but they're strategically placed in areas where the material isn't carrying a primary load, like in the web of stars or ribs. They remove material, saving weight, but often have rolled edges or flanges to maintain stiffness around the hole. Every ounce counts in aviation.
Absolutely. The glossary also lists different aircraft types: amphibian, flying boat, flying wing, delta airplane. Can you give us a quick rundown?
Sure. An amphibian can operate from both land and water, has wheels, and a boat-like hull or floats. A flying boat has a hull designed for water landings, maybe small stabilizing floats, but might not have landing gear for runways.
Like the old Clippers.
Exactly. A flying wing is just basically all wing, no separate fuselage or tail, think B-2 bomber. And a delta airplane has that triangular wing shape like the Concorde or many fighter jets.
And some more unusual ones: autogyro, ornithopter, sailplane.
An autogyro looks a bit like a helicopter, but the main rotor isn't engine-powered. It spins due to the air flowing up through it as the aircraft moves forward, pushed by a propeller. An ornithopter is a theoretical, mostly aircraft that flies by flapping its wings like a bird, and a sailplane is a high-performance glider designed to stay aloft using rising air currents soaring.
Fascinating range of designs. Now, materials. Sandwich material sounds interesting. How does that work?
Sandwich material is a composite structure. You have two thin, strong outer layers called face sheets, maybe aluminum or composite, bonded to a thick, lightweight core.
What's the core made of?
Often it's a honeycomb structure, like aluminum or Nomex honeycomb, or sometimes a rigid foam. The core's job is to separate the face sheets.
Why is separating them important?
It drastically increases the stiffness and resistance to bending, much like an I-beam, but it's incredibly lightweight, because the core material is mostly empty space or very light, high stiffness to weight ratio.
Smart. Using geometry for strength. Now, wood. Seems old school, but it's in the glossary. Annual rings indicating strength.
Yes, in traditional wood construction, the annual rings tell you about the growth rate. Closer, denser rings generally mean stronger wood. You also have to watch out for things like compression wood, which is abnormally brittle, and decay, or rot.
And differentiating hardwood from softwood.
Right. Hardwood from leafy trees, softwood from conifers, different properties. Then there's laminated wood layers glued with grain parallel, and plywood layers glued with grain at right angles for strength in multiple directions.
And lots of potential defects to watch for. Check, knot, pitch pocket, shake, split. You need a good eye for inspection.
Absolutely critical when dealing with wooden structures.
Moving to metals. Clad aluminum. What's the clad part?
Clad aluminum is an aluminum alloy sheet with a very thin layer of pure aluminum bonded to its surface. The alloy provides the strength, but the pure aluminum layer provides excellent corrosion resistance.
Like a built-in protective coating. Clever.
Very effective, especially important in the harsh environments aircraft operate in.
And finally, some high-tech stuff. Kevlar, graphite, Nomex, composites, right?
Exactly. Kevlar and graphite, carbon fiber, are extremely strong, and lightweight fibers used to reinforce composite materials, often in epoxy resins. They allow for complex shapes and significant weight savings compared to metal.
And Nomex?
Nomex is a fire-resistant material. It's often used in honeycomb form as the core in those sandwich panels we talked about, providing structure and fire resistance.
Amazing material science involved. Okay, let's power up and look at power plant and fuel systems. First off, sea-level engine versus altitude engine.
A sea-level engine is rated to produce its maximum power only down low, near sea level. As it climbs and the air gets thinner, its power output drops off significantly.
Makes sense. Less air, less power.
Right. An altitude engine, however, is designed to compensate for that thinner air, usually using a turbocharger or supercharger. These compress the incoming air, forcing more into the cylinders.
So it can maintain its rated power up to a much higher altitude.
Exactly. Crucial for performance at altitude.
Okay. Then we have manifold pressure and the manifold pressure gauge. What's that telling the pilot?
Manifold pressure is the pressure of the air, or air-fuel mixture, in the intake manifold, just before it goes into the cylinders. The gauge shows this pressure, usually in inches of mercury.
And that relates directly to engine power.
Yes, especially in supercharged or turbocharged engines, it's a primary indicator of how much power the engine is developing. More pressure generally means more power.
Got it. Now, something to avoid. Detonation. Sounds bad.
Very bad. Detonation is when the fuel-air mixture in the cylinder explodes violently instead of burning smoothly. It's like hitting the piston with a sledgehammer.
Ouch. What causes it?
Usually excessive heat and pressure in the cylinder. Using the wrong fuel grade is a common cause. That's where octane rating comes in.
Higher octane means more resistance to detonation.
Correct. The rating compares the fuel's resistance to knocking against a mixture of isooctane, rated 100, very resistant, and normal heptane, rated 0, very prone to knocking. Some aviation fuels even have ratings above 100, indicated by a performance number.
So using the right octane fuel is critical to prevent engine damage.
Absolutely. Detonation can destroy an engine pretty quickly if it's severe or prolonged.
Okay, shifting to jet fuel. There's an anti-icing additive. Why is that needed?
Jet fuel can hold a small amount of dissolved water. At high altitudes, where it's extremely cold, this water can come out of solution and freeze into tiny ice crystals.
Which could block fuel filters.
Exactly, leading to fuel starvation. The anti-icing additive, often called FSII, fuel system icing inhibitor, lowers the freezing point of this water, preventing ice formation.
Does it do anything else?
Yes. A second crucial function is that it often acts as a biocide. It kills microbial contaminants, little bugs, bacteria, and fungi that can live in the fuel tanks if there's any water present.
Bugs in the fuel tank? Seriously?
Oh yeah, they can form slimy mats that clog filters and cause corrosion. The additive helps prevent that too. Dual purpose.
Wow. Okay, fuel pumps. What's a compensated fuel pump?
It's a type of engine-driven pump, often vane type, that automatically adjusts its output pressure based on altitude.
How does it do that?
Usually with an internal aneroid or diaphragm that senses ambient air pressure. As altitude increases and air pressure drops, it adjusts the pump's regulating mechanism to maintain a relatively constant fuel pressure difference across the carburetor or fuel control unit.
Why is that constant difference important?
It ensures the engine gets the correct fuel flow for the amount of air it's taking in, regardless of altitude. Helps maintain the right fuel-air mixture.
Clever. Now, for larger aircraft, a manifold cross-feed fuel system sounds complex.
It allows for a lot of flexibility. Basically, all the fuel tanks feed into a common manifold, like a central pipe system with valves.
So you can feed any engine from any tank?
Pretty much, yes. great for managing fuel balance, dealing with a leak in one tank or if one tank's pump fails. Often, the single-point refueling and fuel jettison systems are also connected to this manifold.
Speaking of which, fuel jettison system, why dump fuel?
It's purely a safety thing. Aircraft often have a maximum takeoff weight that's much higher than their maximum landing weight.
Because landing puts more stress on the gear.
Exactly. So if you take off heavy and immediately have an emergency requiring you to land, you might be too heavy. The fuel jettison system lets the crew quickly dump fuel overboard to get down to a safe landing weight.
Makes sense. A necessary safety feature. Where is all this fuel stored? Integral fuel tank and wet wing.
An integral fuel tank means the fuel is stored directly within the aircraft structure, usually the wing, sealed off to make it fuel tight, instead of putting a separate tank bag or container inside.
So the wing structure is the tank?
Essentially, yes. That's why it's often called a wet wing. It saves a lot of weight and space compared to using separate tanks.
Efficient design. Lastly, for fuel, vapor lock. What is it?
Vapor lock is when the fuel, usually gasoline and piston engines, gets too hot somewhere in the fuel lines before the pump or carburetor. It starts to boil and turn into vapor bubbles.
And those bubbles block the flow of liquid fuel.
Correct. It can starve the engine of fuel, causing power loss or even engine failure. More likely to happen on hot days or at high altitudes where the lower air pressure makes fuel boil more easily.
Definitely something to avoid. Okay, let's touch down and talk landing gear and brakes. The oleo shock absorber, how does it cushion the landing?
The oleo strut is pretty clever. It uses both hydraulic fluid, oil, and compressed gas, usually nitrogen or air.
How do they work together?
When the plane lands, the strut compresses. The hydraulic fluid is forced through a small hole, an orifice. This restriction converts the landing energy into heat, absorbing the initial shock.
Okay, that's the damping part.
Right. Then, the compressed gas acts like a spring, absorbing the rest of the impact and preventing the strut from bottoming out. It also helps taxiing over bumps.
So it's a combined damper and spring. What about the centering cam and squat switch?
The centering cam is usually on the nose gear. As the strut extends fully during takeoff rotation, the cam aligns the wheel straight ahead. The squat switch is activated when the aircraft's weight compresses the strut on landing.
What does the squat switch do?
It signals to other systems that the plane is on the ground. Things like preventing accidental gear retraction, enabling ground spoilers, activating anti-skid. Yeah, lots of functions rely on knowing weight on wheels.
Important little switch. What about bungee shock cord? Sounds simpler.
Much simpler, yeah. Found on older or lighter aircraft. It's basically a bundle of rubber strands in a fabric cover, stretched across parts of the gear structure. They absorb shock simply by stretching.
Like giant rubber bands.
Pretty much. Less sophisticated damping than an oleo, but lighter and simpler.
Gotcha. Now, torque links, or scissors, what do they link?
They connect the upper, non-rotating part of the oleo strut cylinder to the lower sliding piston part that holds the wheel axle.
And their job?
They allow the strut to compress and extend freely, but they prevent the lower part, the piston and wheel, from rotating relative to the upper cylinder. Keeps the wheel pointing straight ahead, preventing twisting.
Okay, keeping things aligned. Now, braking. Anti-skid brake system, like ABS in a car.
Very similar principle, yes. It monitors the speed of each main wheel during braking. If a wheel starts to slow down too quickly, indicating an impending skid.
It releases the brake pressure on that wheel momentarily.
Exactly. It rapidly cycles the brake pressure release, apply, release, apply many times per second. This keeps the wheel rotating just below the point of skidding, which actually provides the maximum braking effectiveness.
And prevents tire blowouts and maintains steering control.
Crucial benefits, especially on wet or icy runways.
Now, energizing brake, servo brake versus non-energizing brake, what's the difference in how they work?
It mostly applies to drum brakes, which are less common now on larger aircraft. An energizing or servo brake uses the rotation of the brake drum itself to help apply the brakes harder.
How?
The way the brake shoes are arranged, the rotating drum tends to wedge one shoe tighter against the drum, and that force helps apply the other shoe. It's a self-boosting effect.
So less pedal effort needed.
Right. A non-energizing brake doesn't have that servo effect. The braking force is directly proportional to the force applied by the pilot or hydraulics, more common in disc brakes.
Okay. What causes dragging brakes or spongy brakes? Common issues.
Dragging brakes are when the brakes don't fully release after you let off the pedals. Can be caused by blocked return ports in the master cylinder or mechanical issues in the caliper, leads to overheating, and wear.
And spongy brakes. Feels like stepping on a sponge.
Usually caused by air trapped in the hydraulic fluid lines. Air is compressible, oil isn't. So when you press the pedal, you compress the air instead of applying full force to the brakes. Needs bleeding.
We'll get to bleeding later. What about fading of brakes?
Brake fade is a temporary loss of effectiveness due to overheating, usually from heavy or prolonged braking.
What happens when they overheat?
Several things. The brake drum might expand away from the shoes in a drum brake. The friction material itself can overheat and lose its coefficient of friction. Or the hydraulic fluid could even boil if it gets hot enough, causing vapor lock in the brake lines.
Overheating is the enemy of brakes, clearly. For bigger planes, multiple disc brakes are used. How do they handle the heat better?
They have a stack of alternating rotating discs, keyed to the wheel, and stationary discs, keyed to the axle. When you apply the brakes, a pressure plate squeezes this stack together.
So lots more surface area for friction.
Exactly. More surface area means the heat generated is spread out more, and they can absorb and dissipate much more energy than single disc or drum brakes. Essential for heavy, fast aircraft.
Makes sense. Now, on the tires themselves, fusible plugs. What do they fuse?
They're a safety device in the wheel hub, mainly for tubeless tires on high-performance aircraft. If the brakes overheat massively, say during a high-speed rejected takeoff.
The heat transfers to the wheel and tire.
Right. The air pressure inside the tire can rise dangerously high, risking a tire explosion. The fusible plug has a core material that melts at a specific temperature.
And lets the air out safely.
Yes. If the wheel gets too hot, the plug melts, and the tire deflates in a controlled way, preventing a blowout.
A thermal fuse for the tire. Clever. Landing on wet runways brings the risk of hydroplaning.
Yes, a very dangerous situation. If there's enough water on the runway and the plane is going fast enough, the tires can ride up on a thin film of water, losing contact with the pavement.
Like water skiing.
Essentially, yes. And when that happens, you lose almost all braking effectiveness and steering control. Very hazardous.
Definitely want to avoid that. What about wheel alignment? Toe in and toe out?
This refers to the alignment of the main wheels when viewed from above. Toe in means the front edges of the tires are slightly closer together than the rear edges. Toe out is the opposite.
Why is the correct toe setting important?
For stable ground handling, taxiing, takeoff, roll, landing, roll out, and to prevent excessive tire wear from the tires scrubbing sideways, needs to be set correctly.
Right. Finally, nose wheel shimmy and the shimmy damper. What's that vibration?
Shimmy is a rapid side-to-side oscillation or vibration of the nose wheel, usually during taxiing. It can be quite violent sometimes.
What causes it?
Imbalance in the wheel, looseness in the steering linkages, geometry, various factors. The shimmy damper is basically a small hydraulic shock absorber built into the nose gear steering mechanism.
And it just damps out those oscillations.
Exactly. It resists rapid side-to-side movements, keeping the nose wheel tracking smoothly.
Good. Okay, let's switch gears completely to the aircraft's nervous system. Electrical and avionics. Starting basic, current, EMF, conventional current, electron current.
Okay. Current is the flow of electric charge, like water in a pipe. Electromotive force, or EMF, is the electrical pressure that drives the current, measured in volts.
Like the pump pushing the water.
Good analogy. Now, conventional current is the historical idea that current flows from positive to negative. It's still used in many diagrams.
But that's not what actually happens in wires.
Not usually. In metal conductors, it's negatively charged electrons that move. They flow from the negative terminal to the positive. That's electron current. Just a convention difference, but good to know both exist.
Right. Now, fundamental components. Circuit breaker, fuse, relay, solenoid contactor, diode, transistor, NPN, PNP, Zener diode, SCR. Quick rundown.
Okay, circuit breakers and fuses protect circuits from too much current. Breakers can be reset. Fuses blow and need replacing. Safety devices.
Got it. Relay.
An electrically operated switch. A small current in a coil operates contacts to switch a larger current elsewhere.
And a solenoid.
Uses an electromagnet coil to create linear motion, pulls a plunger in or pushes it out. Used to operate valves, latches, things like that.
Contactor sounds similar to a relay.
It is basically a heavy-duty relay designed for switching very high currents, like connecting the battery to the main electrical bus.
Okay, diode.
A one-way valve for electricity lets current flow in only one direction. Semiconductor device.
Transistor.
Also semiconductor. Can act as an electronic switch or amplify a signal. NPN and PNP are just two different types based on their internal structure.
Zener diode.
A special diode designed to conduct backwards at a specific voltage, used for voltage regulation.
And SCR silicon-controlled rectifier.
It's like a diode that only turns on when you give it a small trigger signal to its gate. Once it's on, it stays on until the main current stops. Used as a solid-state switch.
Quite the toolkit of electrical parts. How are they connected? Series circuit, series parallel.
In a series circuit, components are connected end-to-end, one path for current. If one breaks, the whole circuit stops.
Like old Christmas slave.
Exactly. In a parallel circuit, components are connected side by side, multiple paths. If one path breaks, the others can keep working. Most aircraft lighting is parallel.
Reliable.
Definitely. And a series parallel circuit is just a combination, some parts in series, some in parallel. Allows for more complex designs.
Okay. Generating power in flight.
Right.
Generator versus alternator. And generator series and shunt fields.
Both convert mechanical energy from the engine into electrical energy. A traditional generator usually produces direct current, DC. An alternator produces alternating current, AC.
Why the two types?
Historically, generators were common. Their output voltage is controlled by varying the current in their magnetic field windings. The series field winding carries the main output current. The shunt field winding is in parallel and used for voltage regulation.
And alternators.
They're generally lighter and more efficient, especially at low engine speeds. Most modern aircraft use alternators. The AC they produce is often converted to DC for systems that need it, using a transformer rectifier unit, or TRU.
So alternators are more the standard now. The master switch sounds important.
It is. It's the main switch connecting the battery to the aircraft's electrical bus, the main distribution system. Often it also controls the alternator or generator field circuit.
So it turns the whole electrical system on or off?
Essentially, yes. The first switch you turn on, the last one off. Crucial for safety and control.
Right. What about bonding and shielded wire? Why are they needed?
Bonding is electrically connecting all the separate metal parts of the airframe together with wires or straps.
Why do that?
Several reasons. Provides a common ground return path for electrical systems. Prevents static electricity buildup, which can cause radio noise or sparks. And ensures fault currents can flow back to trip breakers properly. Very important for safety.
Okay. And shielded wire?
That's wire with a conductive braid or foil layer around the inner conductor, underneath the outer insulation.
What does the shield do?
It blocks electromagnetic interference, or EMI. Stops external noise getting into the wire, and stops signals in the wire radiating out and interfering with other sensitive electronics, like navigation or communication radios. Critical for avionics.
Protecting the signals. Now, speaking of avionics, that huge list of acronyms, ADC, ADF, ADI, EADI, ADA, ICAS, AFACES, FMC, HSI, IRS, IRU, MFD, RMI, TCAS, TMC. Whoa! These are the glass cockpit systems.
Many of them are, yes. They represent the electronic flight instruments and management systems. It's a lot, but basically. ADC, Air Data Computer, calculates airspeed, altitude from sensors. ADF, Automatic Direction Finder, points to ground radio beacons called NDBs.
Older nav system.
Yeah, simpler. ADI, Attitude Director Indicator, shows pitch and roll, now mostly replaced by EADI, Electronic ADI, on screen. EHSI, Electronic Horizontal Situation Indicator, shows heading, course, nav info, replaces the older mechanical HSI.
Okay, so EADI and EHSI are core parts of EFI, Electronic Flight Instrument System.
Exactly. EFIS is the whole suite of screens replacing old dials. ELAKS is engine indicating and crew alerting system, displays engine data and warnings. FMC is the flight management computer, manages flight plans, performance calculations.
The brain of the flight plan.
Pretty much. IRS, Inertial Reference System, uses gyros and accelerometers in the IRU, Inertial Reference Unit, to calculate position and attitude without external signals. Very accurate. MFD is multifunction display, can show maps, weather, systems info. RMI, radio magnetic indicator, combines heading with needles pointing to VOR NDB stations.
More navigation aids.
Right. TCAS is traffic alert and collision avoidance system to detect other aircraft and warns pilots. Hugely important safety system. And TMC's thrust management computer helps manage engine power settings.
A lot of computing power helping the pilots? What about the ELT, Emergency Locator Transmitter?
That's a safety beacon. If the aircraft crashes, impact forces are supposed to activate the ELT, which transmits a distress signal on emergency frequencies. Search and rescue teams use the signal to find the wreckage. Modern ones include GPS coordinates, too.
Hopefully never needed, but vital if it is. Oxygen systems. Continuous flow, diluter demand, pressure demand, and the rebreather mask. Different needs at different altitudes.
Yes. Continuous flow provides a constant oxygen supply, often used with a rebreather oxygen mask, which saves some exhaled oxygen in a bag to mix with the fresh supply, conserves oxygen at lower altitudes.
Okay. Diluter demand.
Only supplies oxygen when you inhale, and it mixes oxygen with cabin air based on altitude. More efficient. Standard in airliners.
And pressure demand.
For very high altitudes. The air pressure is so low, even 100% oxygen isn't enough. This system actually forces oxygen into the lungs under positive pressure, needed for military pilots, for instance.
Different systems for different pressure environments. Carbon monoxide detector, why is that needed?
Carbon monoxide, CO, is a deadly odorless gas produced by incomplete combustion. In piston aircraft, a leak in the exhaust system could let CO into the cabin heater. The detector warns the pilot if CO levels become dangerous.
Vital safety device for piston planes. Fire detection.
Yeah.
Continuous loop and thermocouple systems. And fire pole handle, fire zone.
Continuous loop systems use a tube or wire running through fire-prone areas, like engine compartments, fire zones. Heat from a fire changes the electrical properties of the loop material, triggering an alarm.
Okay, and thermocouple systems.
Use junctions of dissimilar metals, thermocouples, placed in fire zones. Heat generates a voltage difference, which triggers the alarm if the temperature rises rapidly. Both detect fires quickly.
And the fire pole handle.
In the cockpit. Pulling it for a specific engine shuts off fuel, hydraulics, electrics to that engine, and usually arms or fires the extinguishing agent into that fire zone. Drastic action for a serious emergency.
Critical response system. Overvoltage protector guards against what?
Protects the electrical system from the generator or alternator, producing too high a voltage, which could damage sensitive electronics.
Yeah.
If voltage goes over a set limit, it trips the generator or alternator offline.
Electrical safety net. Lastly here, stroboscopic tachometer and the nav aids VOR and VORTAC.
A stroboscopic tachometer uses a flashing light to measure RPM, often for propellers. When the flash rate matches the rotation speed, the object looks stationary. VOR is very high-frequency omnidirectional range, a radio beacon giving directional bearing from the station. VORTAC adds military TACAN distance measuring capability to the VOR bearing, key navigation aids.
Measuring speed with light, navigating with radio. Cool. Let's dive into hydraulic and pneumatic systems. First, the basic difference. Hydraulics versus pneumatics.
Both use fluid power. Hydraulics uses liquids, usually specialized oil, which are virtually incompressible. Pneumatics uses gases, usually compressed air or nitrogen, which are compressible.
And that difference matters how?
Hydraulics can transmit very large forces accurately because the fluid doesn't compress. Great for landing gear, flight controls, brakes. Pneumatics is often lighter, simpler, cleaner, but less precise, and usually for lower force applications, like some instrument gyros or de-icing boots.
Liquid power versus gas power. And Pascal's law is key for hydraulics.
Absolutely fundamental. Pascal's law says pressure applied to an enclosed fluid is transmitted equally in all directions.
How does that help?
It allows force multiplication. Apply a small force to a small piston. The pressure created is transmitted through the fluid to a larger piston, which produces a much larger output force. That's how you move heavy landing gear with manageable input forces.
The magic of hydraulic leverage. Okay, components. Accumulator, actuator types, pump types, selector valve types, check valve, relief valve, pressure regulator, restrictor, shuttle valve, sequence valve, unloading valve. Wow, another big list.
Yeah, the building blocks. An accumulator stores hydraulic fluid under pressure, dampens pulses, provides emergency pressure. An actuator converts fluid pressure into motion.
Linear for straight motion, rotary for turning.
Right. Double-acting uses pressure for both directions. Single-acting uses pressure one way, spring return usually. Rack and pinion is a type of rotary actuator.
Pumps create the flow. Constant versus variable displacement.
Yep. Constant displacement pumps move a fixed amount of fluid per revolution, like gear or gerotor pumps. Need an unloading valve or regulator. Variable displacement pumps adjust their output flow based on system demand, more efficient. Hand pump for manual backup.
Selector valve directs the flow. Open center versus closed center.
Exactly. Directs fluid to the desired actuator. Open center lets fluid flow back to reservoir when neutral. Closed center blocks flow when neutral, requires a pressure regulator or variable pump.
Check valve, one-way flow.
Correct. Relief valve protects against overpressure by dumping excess back to reservoir. Pressure regulator maintains a set pressure. Absolute type reference is vacuum. System pressure type reference is ambient or system return.
Restrictor slows flow. Shuttle valve selects between two pressure sources like normal and emergency.
Yes. Sequence valve makes things happen in order, like gear doors open before gear comes down. Unloading valve lets a constant displacement pump idle under low load when pressure's built up. Saves energy.
A very complex system of control. What's a hydraulic fuse?
It's a safety device. If a hydraulic line bursts and fluid starts flowing out too fast, the fuse detects the high flow rate and shuts off the line.
To prevent losing all hydraulic fluid.
Exactly. Tries to preserve fluid in the rest of the system.
Important safety backup. We hear about Skydroll hydraulic fluid. What's special about it?
Skydrol is a common brand of synthetic phosphate ester-based hydraulic fluid. Its main advantage is fire resistance, unlike mineral oil-based fluids. Also works over a wide temperature range and is compatible with seals used in high-pressure systems.
Fire resistance is a big plus in aircraft. Now, bleeding of brakes, we talked about spongy brakes earlier, this fixes it.
Yes. Bleeding is the process of removing trapped air from the hydraulic brake lines. You force fresh fluid through the system, opening bleed valves of the calipers to let the air and old fluid out until only solid, air-free fluid emerges.
Restores that firm pedal feel.
And full braking power. Essential maintenance.
What's case pressure in hydraulic pumps?
Some pumps have a housing, a case, that needs to be kept full of low-pressure fluid for lubrication and cooling of internal parts. Monitoring the pressure in this case drain line can indicate the health of the pump's internal seals. A sudden increase might mean an internal leak.
A diagnostic check.
Okay.
Pneumatics. Dry air pump versus wet type vacuum pump and filter separators.
Dry air pumps, often used for instrument gyros, use self-lubricating carbon vanes. They need very clean, filtered air to avoid damage. Wet-type pumps use steel vanes lubricated by engine oil.
So the exhaust air from a wet pump has oil in it?
Yes. Needs an oil separator to remove the oil before the air is vented or used. Both types need good inlet filters to keep dirt out.
Managing the air and oil. Finally, moisture separator and orifice check valve in pneumatics.
Compressed air contains water vapor. As the air cools expanding through the system, water condenses out. A moisture separator removes this liquid water to prevent freezing or corrosion in components. An orifice check valve allows free flow one way, but restricted, through a small orifice, flow the other way, used to control the speed of pneumatic actuators sometimes.
Controlling water and flow speed. Okay, deep breath. Let's move to finishing and maintenance. Aircraft finishes. Dope, lacquer, enamel, varnish. Different types of paint.
Sort of. Dope is specific to fabric aircraft. It's a cellulose nitrate or acetate solution that shrinks the fabric taut as it dries and provides protection. Lacquer is a fast-drying solvent-based finish, often glossy. Enamel is typically a slower-drying paint, often oil-based or synthetic, forms a hard finish. Varnish is a clear protective coating, usually for wood.
And utility finish versus show-type finish.
Utility is functional, provides protection, maybe not perfectly smooth. Show type is conquers quality many layers, lots of sanding and polishing for a flawless look. Very labor-intensive.
Got it. And issues with dope? Bleeding, blush, dope proofing, roping, rejuvenator, UV blocking dope.
Bleeding is when underlying colors seep into the dope. Blush is a milky look, caused by moisture during drying. Dope proofing protects underlying stuff from dope solvents. Roping is uneven application. Rejuvenator softens old, brittle dope. UV blocking dope protects the fabric from sunlight damage.
A whole science to fabric finishing. What about primer and plasticizer?
Primer is the base coat. Helps the top coat stick and often provides corrosion protection on metal. Plasticizer is added to finishes like dope to keep them flexible so they don't crack when the structure flexes.
Flexibility is key. Plastic media blasting. PMB, what's that used for?
It's a way to strip paint off aircraft surfaces. Uses fine plastic beads repelled by air. It's gentle enough not to damage the underlying aluminum skin, unlike harsher methods like sandblasting.
A gentler way to get down to bare metal, fabric repairs, surface tape, bias cut, pinked edge, reinforcing tape, anti-tear strip, and rib lacing. More specialized stuff.
Yeah, surface tape or finishing tape goes over seams, patches, and rib lacing for a smooth finish. Bias cut tape stretches for curves. Pinked edge has serrated edges to prevent fraying. Reinforcing tape goes under the fabric covering over the ribs to strengthen where the rib lacing, stitching the fabric to the ribs, goes. Anti-tear strips add more strength under the reinforcing tape in high-stress areas.
Lots of layers and stitching to keep the fabric secure. For metalwork, the Cleco fastener. What's that little thing?
Clecos are brilliant temporary fasteners. You drill holes for rivets, then insert Clecos to hold the metal sheets tightly together in perfect alignment while you install the permanent rivets. Then you just pop them out.
Like temporary metal staples. Very handy. Countersinking and dimpling, coin, radius, hot thermal. These are for flush rivets.
Exactly. To make the rivet head sit flush with the skin for smooth airflow. Countersinking cuts a conical recess for the rivet head. Dimpling uses dies to form a depression in the metal sheet itself. Coin and radius are types of dimpling dies. Hot dimpling heats the metal first for harder alloys to prevent cracking.
Different ways to get that smooth finish. Joining methods, riveting, welding, migma, tajita, polarity, flame types, brazing, soldering, tack weld, rosette weld, lots of ways to join metal.
Riveting is mechanical fastening. Welding melts the base metal, often with filler, to fuse parts. MIG, metal inert gas, or GMAW, uses a continuous wire electrode and shielding gas. PIG, tungsten inert gas, or GT, uses a non-consumable tungsten electrode, maybe filler rod, and shielding gas very precise.
And polarity and flame types.
In DC welding, polarity matters for heat control. In gas welding, the flame, neutral, oxidizing, carburizing affects the heat and chemical reaction. Brazing and soldering use filler metals that melt below the base metal's melting point, like gluing with molten metal. Brazing is hotter than soldering. Tack welds are temporary holds. Rosette welds join overlapping sheets through a hole in the top one.
Choosing the right method for the right joint is key. Sheet metal bending. Bend radius, bend tangent line, setback, K-factor, relief hole, cornice break. Precision terms.
Absolutely. Bend radius is the inside radius of the curve. Bend tangent line is where the curve starts. Setback helps calculate the flat pattern length needed. K-factor relates to how material stretches in a bend for precise calculations. Relief holes prevent tearing at corners where bends meet. A cornice break is a machine for making straight bends in sheet metal.
Geometry and calculation needed for accurate parts. Finally, maintenance procedures and documentation. Annual inspection, progressive, pre-flight, compass swinging, AD notes, Form 337, troubleshooting, MTBF, testers, hydrostatic test, MSDS, shelf life. Phew.
Okay, rapid fire. Annual is a required yearly deep inspection. Progressive breaks the annual into phases. Pre-flight is the pilot's check before flying. Compass swinging adjusts the compass to correct for local magnetic fields in the aircraft. AD notes, airworthiness directives, are mandatory fixes for known safety issues. Form 337 documents major repairs alterations. Troubleshooting is diagnosing problems. MTBF, mean time between failures, is a reliability metric.
Testers like continuity tester, multimeter, clamp-on ammeter are for electrical checks.
Yes. Hydrostatic test, pressure test cylinders like oxygen tanks. MSDS, material safety data sheets, detail chemical hazards in handling. Shelf life is how long a product like sealant is good for in storage.
A whole system ensuring aircraft stay safe and well-maintained. Okay, final push. Measurement and navigation in general aviation terms. Flight instruments. Airspeed indicator, altimeter, aneroid, Colesman window, attitude indicator, heading indicator. The basic six-pack almost.
Pretty much the core instruments. Airspeed indicator shows speed relative to the air using pedostatic pressure. Altimeter shows altitude based on air pressure using a sealed capsule called an aneroid. The Colesman window lets you set the current barometric pressure for accuracy. Attitude indicator, artificial horizon, shows pitch and roll. Heading indicator, directional gyro, shows magnetic heading more stably than a simple compass.
Giving the pilot the essential picture. Different airspeeds, CAS, TAS, position error, and pressure altitude.
Indicated airspeed has errors. Correcting for instrument and position error due to airflow disturbance near the static port gives calibrated airspeed, CAS. Correcting CAS for air density changes with altitude and temperature gives true airspeed, TAS, your actual speed through the air mass. Pressure altitude is what the altimeter reads when set to the standard pressure of 29.92 inches of mercury used for performance calculations.
Different speeds for different purposes. What about Mach number, subsonic, transonic, hypersonic, speeds relative to sound?
Yep. Mach number is your speed divided by the local speed of sound. Below Mach 1 is subsonic. Around Mach 4.8 to 1.2 is transonic, tricky airflow with mixed subsonic, supersonic flow. Significantly above Mach 1, usually Mach 5 plus, is hypersonic. Speed regimes, navigation basics, magnetic bearing, isogonic line.
Magnetic bearing is direction relative to magnetic north. An isogonic line on a chart connects points with the same magnetic variation, the difference between true north and magnetic north. Used to convert between true and magnetic bearings.
Correcting the compass. We mentioned VOR and VORTAC. What's a radial and a waypoint?
A radial is one of the 360 magnetic courses radiating out from a VOR station. You navigate by tracking specific radials. A waypoint is just a defined geographic point in space, usually defined by latitude-longitude, used for RNAV or GPS navigation. You fly from waypoint to waypoint.
Points in space versus bearings from a station. Older systems. LORAN, NDB, RDF, goniometer, null position. LORAN was a long-range radio nav system using timed signals from ground stations. NDB, non-directional beacon, is a simple ground transmitter. RDF, radio direction finding, is using an antenna on the plane. Goniometer is a type of electronic RDF antenna to find the bearing to the NDB, often by finding the null position where the signal is weakest.
Early electronic navigation. DME, ROCU, azimuth.
DME, distance measuring equipment, gives slant range distance to a ground station, often paired with a VOR. IRS, inertial reference system, uses gyros and accelerometers in the IRU, inertial reference unit, to calculate position completely independently, no external signals needed. Azimuth is just a horizontal angle or bearing, usually measured clockwise from north.
Self-contained navigation is impressive. GPU, ground power unit.
That's the cart that plugs into the plane on the ground to provide electrical power for systems checks, engine starting, etc., without using the plane's battery or running engine's APU.
Keeps things powered up on the ramp. Okay, lightning round. General aviation terms. Just hit the key ones.
Okay, aborted takeoff. Stop before lifting off. Absolute pressure, relative to vacuum, absolute zero, lowest possible temp. ARINC, Aviation Communication Standards, body. AWG, wire size standard. YD, built-in self-test, calendar month. FAA definition for time limits. CG, center of gravity, balance point, center of lift, where aerodynamic force acts, conventional current, plus to flow assumption, critical pressure temp, point where liquid gas phases merge, dynamic pressure, Q, pressure due to airflow speed, elastic limit, point before permanent deformation, foot-pound, unit of energy work, force, push-pull, FSDO, FAA, Flight Standards District Office, flashpoint, lowest temp, a liquid gives off ignitable vapor, foot-pound, digit known as CARES, nose to tail, pitch, major alteration repair, significant work needing specific paperwork, mean camber, longitudinal axis, nose to tail, pitch, major alteration repair, significant work needing specific paperwork, mean camber, average airfoil curve, MSL, mean sea level moment, rotational force effect, NAP, fabric, fiber direction, negative pressure relief.
Prevents cabin pressure going below ambient. Neutral axis. Line into bent beam with no stress. Partial pressure. Pressure of one gas in a mixture. Pitch. Nose up-down rotation. Roll. Wing up-down rotation. Potential energy. Stored energy. Power. Rate of doing work. Pre-flight. Pilot's walk-around check. Relative wind. Airflow direction relative to the wing. Repair. Fixing damage. RPM. Revolutions per minute, sensible heat, changes temperature, latent heat, changes state, for example, ice to water, shear strength, resistance to slicing forces, steel well. Short takeoff and landing, strain, deformation under stress, stress, heating vapor above boiling point, surfactant, reduces surface tension, torque, twisting force, trim flight, hands-off stable flight, vertical axis, up-down through CG, nose, left-right rotation, yield strength, stress-causing permanent deformation, shoe.
Wow. That glossary really covers the gamut, doesn't it? From basic physics to complex systems.
It really does. And what's fascinating is how interconnected it all is. You start with an airfoil that leads to lift and drag, which relates to angle of attack and stall strips, which are part of a wing structure involving spars and stressed skin, made of clad aluminum or composites, controlled by ailerons, using hydraulics powered by pumps, monitored by avionics. It just keeps going.
It's a web. Each term unlocks another part of the system. It's not just words. It's a blueprint, like you said, of this incredibly engineered machine.
Exactly. Connecting those dots gives you a real appreciation for how flight works and the ingenuity involved.
Absolutely. So to our listener, we hope this deep dive has helped make sense of these terms. But really, go back to that glossary. Pick an area that sparked your interest, maybe hydraulics, maybe materials, and just explore further. Each term really is a doorway.
Yeah, definitely. And it makes you wonder, doesn't it? We see this incredibly detailed, precise language just for aviation. What other fields have lexicons that are just as intricate, just as fascinating?
That's a great question. Medicine? Law?
Maybe specialized crafts?
Could be anything, really. High on cooking. Theoretical physics. We'd love to hear what you think. Maybe you even know of a glossary or source from another field that would make for a great future deep dive. Let us know.